We forgot all the makeup, but it's okay.
Okay. There you are.
Okay. Okay, thank you all for coming, and thank you to the remote sites as well. It's a pleasure to have here today Professor José Moura from Carnegie Mellon. Professor Moura had his undergraduate degree from the Institute Superior Técnico de Lisbon and his graduate degrees from MIT. He's currently on sabbatical at MIT, and he's the co-founder of a center for critical infrastructure research, which is a big topic and a hot topic these days. And he's the president-elect of the IEEE Signal Processing Society, and he serves on many committees and the boards of IEEE. It's a pleasure to have you here. Thank you. The floor is yours.
Thank you very much. Well, it's a pleasure to be here, and thank you, Hamid, for inviting me. The topic is distributed inference, and I'll explain what I mean by topology optimization. This is work done with students. Soumya Kar, Saeed Al-Dosari. He's back in Saudi Arabia. He's a professor there. And there were several grants that supported this work. So let's see if I can do this. Apparently not.
I think you have, yeah, that pointer, I think you have to do it on the laptop.
I have to do it, okay.
Yeah.
So I'll do that. Okay, so basically I'm going to go through a few topics here. First, I'll try to motivate the problem. So that's the first topology design. And then I'll consider 3 or 4 classes of problems. So going from the simpler version of the problem to a more complex version of the problem. Essentially, this one that I call the non-random topologies will lead to a solution that we will say it's like an analytical solution. It's really not an analytical solution, but you can specify what is the topology of the network. You can say belongs to a certain class for which you have methods to construct the topology. And as you move down, you will get more complex, more practically oriented versions of the problem, but the types of solutions you get, for example, in this last class, is really a kind of an algorithmic solution. So you have to run a computer to come up with the solution, okay? So let's get started. And what do we mean by topology? So suppose that you have some physical space and you drop a bunch of sensors, and the question is how these sensors make measurements and they do some local processing. We are going to assume what's called a flat network, which means there is no sensor that is more powerful than the other sensors. Though the sensors are more or less all of the same type, and they are all kind of dumb sensors constrained by power and communications and so forth. So, and the question is, you want to reach some agreement between the sensors about the state of the environment, and you want the sensors to cooperate, so to talk among themselves, okay? And that's the topology really means, should they talk, say, should they communicate among themselves as these blue lines or black lines here suggest, meaning that this sensor talks to that sensor and to this sensor and to this sensor, but not to the others? Or should they talk in a different way, for example, like this red one, okay? And so by the topology design, what we mean is what's the infrastructure, the communications infrastructure, that network that supports the communication among these different sensors. That's the problem that we are going to try to address in this talk. Let me set up the problem a little bit more. So because I'm focusing on the topology design, I'm going to simplify. I'm going to consider a very simple problem that I'm addressing, okay? So I'm not going to consider a very complicated detection problem or classification. I'm going to try to stay as simple as possible in terms of the problem that the sensor network is supposed to solve. Okay, so this and the model underlying it also is going to be very simple. So the difficulty or the interest in the talk is more in terms of the problem that we address of topology design. Okay, so the sensors make measurements, and let's say that these are the measurements, and we collect them, say, in a big vector. So we stack all these measurements, and all we care is that these sensors are trying to determine the value of some property P, and we are going to say it's a binary value. So it's a binary detection problem. Okay, very simple. So say that the sensors are measuring temperature, and we are saying it's hot or it's cold, or they are monitoring some physical space, and they are trying to say, did someone enter the space or not? Okay, so those types of very simple global type question. And this is jargon here, but let me say what it is. So we capture the topology and the problem of topology design by a graph. Okay, and the nodes of the graph are, of course, where the sensors are, and the edges in the graph are the lines that you put between the sensors, connecting the sensors. So these are where I have an edge, a sensor can communicate with the other sensor. Now, we are going to simplify again in terms of the structure by saying that if this sensor communicates with that sensor, then that sensor can communicate with the other one. Okay, so there is a reciprocity here in terms of this communication, and that's captured by saying the graph is undirected. So you could have other types of graphs where you'd have arrows pointing from this to that one, which would mean that this sensor would communicate with that, but not vice versa. Okay, but that's not the case here. We also rule out the fact that you have self loops. So it doesn't really make much sense to say that the sensor communicates with itself. The sensor knows what's going on there, so it doesn't need to broadcast to receive what. Okay, so you rule out that, which in terms of graphs also makes life easier. And the other thing is a connected graph. So we are looking for a topology where every sensor can eventually communicate with every other sensor by a multi-hop. Okay, but you don't have two different clusters, for example, saying that these sensors can talk among themselves and these among themselves, but this cluster doesn't communicate with that. Okay, so that's called a connected graph. Okay, and so that's the problem. So let's see examples of topologies that people usually consider when you look at, okay, let's look at the sensor network, and people come up with solutions like this. Well, they can say the star network, okay, the star network is one where you elect one of the sensors to be a fusion center, okay, so it collects all the data from all the other sensors and does all the work, which for a flat network is not very useful, it's not very good. Because first of all, this doesn't have more power than the others according to our assumption, and so you were burdening one sensor, and that sensor might use all the resources, all the power available, and then the sensor doesn't come. Then the sensor network dies just because that sensor there dies. Okay, but it's very efficient in terms of the number of links or communication channels that you have. So people. There are many applications where people do consider this type with a fusion center, where maybe that one is more powerful than others. But we are not interested in that type of network. Another one is, for example, this one, where every sensor talks to every other sensor. So that's then the problem here is that, of course, as the number of sensors n gets large, then you have to establish lots of communication channels. The number of communication channels grows with n squared, and of course that's not a good solution either. Or you could say, okay, let me go through a sequential scheme, and this has lots of problems, because if any link here breaks down, then the communication breaks down. The solution is only there, so you have to hop through all of them, so it's not also very interesting. But these are many architectures that people have considered. So let me try to come back to my problem of topology design, but now you understand that what I'm looking is for where to place the edges of my graph. And of course we want a robust solution, so we don't want a star parallel kind of architecture where you elect a fusion center. That's not very robust. You want local communication, so you want to rule out the fully connected, the complete graph where everybody talks to everybody. That requires global communication. You don't want that. As I mentioned, you do want a connected graph, okay? Even if it's through multi-hops, you do want connected graph. We are going to solve this problem, as I said, in a very simple detection problem. We want to solve it in a distributed fashion. We don't want to have a fusion center. We want the sensors that can communicate among themselves to communicate several times among themselves, iterate. So it's going to be an iterative algorithm that essentially is going to implement in a distributed fashion a kind of a centralized algorithm, okay? So, but implemented in a distributed fashion. And then there are all these simplifying assumptions. It's a conditional independent observation. So the measurements that I make, if I know the state of the environment, then the measurements are independent. It's like noise is the only thing that distinguishes them. And what essentially is going to be is the type of processing that's going to go. So each sensor is going to do some local processing, essentially computes what's called, for those of you that are familiar with that, computes what's called a likelihood ratio based on their measurements, computes some quantity. For those of you familiar with the term, let's call it a likelihood ratio. And then that's the starting point of the computation of the algorithm, and then they interchange that information. And as they interchange, they do some additional computations, and so the knowledge or what's going on at each sensor evolves with time, and we are going to call that the state of the sensor. Okay, so the state starts by being the likelihood ratio, and then as time goes on, the state evolves, and we'll show how it evolves. And in the end, every sensor is going to reach a conclusion, and hopefully that conclusion is and they do that in some good sense. So let me just, if you are not familiar with detection, I'm sorry about that, because this is just an introductory slide. The key step is this. It has nothing to do with detection. But for those of you that know a little bit about detection, so the problem really, if it was a centralized problem, what we would have is all our measurements stacked in a big vector, and very simple. We are simply distinguishing between, say, hot and cold, okay? Some m or some minus m, and this is noise. And standard assumptions, of course this is a very simple one, and you construct what's called a likelihood ratio. You construct a sufficient statistic. That's what I meant. A sufficient statistic, which is essentially some big vector multiplying the big vector. So this is a scalar. So you have to do this computation if it was a fusion center. Okay, that's what you do. And basically, you can look at this, and you can reorganize these computations. And essentially, what this sufficient statistic is doing is kind of averaging the local likelihoods at each sensor, that each sensor construct at initial step. From their own observation, sensor yn constructs its likelihood, and then what you really would like to is construct this, which is simply the average of these numbers. So for those of you that are not detection freaks, the only thing you need to understand is that what the algorithm is going to do is simply computing the average of the initial states at each sensor. Okay, so each sensor has a number, and what you want to do is simply combine and average those numbers in a distributed fashion. So you are not going to send that number to the fusion center. So you are going to do that by talking locally with the people you can talk. And so that's the problem, really. Okay, and this is called a distributed averaging algorithm, okay? And it's a weighted algorithm. So the way you do that is you are going to weight. I'm sorry, this is still the likelihoods. So you do that averaging. Let me illustrate here, for example, what happens. So let's say that these are three sensors, very simple, okay? and with their measurements they construct their original likelihood, okay, and that's the original state, x1 of 0, x2 of 0, x3 of 0. So these are computed from the measurements, from the local measurement available at each sensor. And what you are going to do then is then suppose that the topology was like this. So this sensor sends to that one and to that one, and once, say, x3 receives the current state of sensors 1 and 2, so builds its next state. So now I've already done this for, say, I iterations. It constructs the state at I plus 1 iteration of x3 by a weighted average of the states that it received from the other two, so x2 and x1, plus a weight also on my own. This is the algorithm for it. This is the distributed algorithm that is going to compute that sum that we had before. Okay, that's a way of constructing this. And by the way, I didn't refer here, but these types of algorithms and convergence of these iterative algorithms and so forth, early work on this was John Cicicli's thesis in 1983 or 84. Okay.
So you do that at each node?
Yeah, you do that at each node. Each node talks to the neighbors, let's call it that way, weights the information, recomputes the state, rebroadcasts the state.
And you decide about the neighborhood.
I'm sorry?
You decide about the neighborhood that you're...
Yeah, that's what I want to do, is design the neighborhood. Okay, neighborhood structure, understood. And then once the number of iterations goes a sufficient number of times, each sensor simply thresholds the state and makes a decision, is it H1 or H0. Okay? Now, you could analyze the performance for a given network. You can analyze the performance of this algorithm. You can compute the probability of error. Okay? And again, this is going back for those of you who know detection. But just to show convergence, you can show that in fact the distributed algorithm that I described, that I'm representing here now in matrix format, so I stack the states of all the sensors, and this is at the iteration I, this is at iteration I plus 1, and those W's that weight the information that I receive from the different sensors are in this big matrix W. Okay, so this is a big matrix, so n by n. Okay, this W matrix is a highly sparse matrix because you only allow communication among a few sensors at a time. Okay, so this W is a highly sparse matrix. But you could analyze this, and you could show that for the distributed algorithm versus the centralized one, this probability of error, as the number of iterations goes to infinity, this one actually converges to that one. Okay, and this under very mild assumptions on the type of topology that you have here. As long as it's connected and a few other minor assumptions, this is going to converge to that. So the problem of topology design is not the problem of coming up with a topology such that the performance of this one approaches the performance of that one, because under very mild conditions, this converges to that one. Okay, so what's the problem? The problem is the rate at which you converge. Okay, there are topologies for which this convergence here is very slow, and there are topologies for which the convergence is very fast. And what you want is to come up under the same constraints that we are going to impose on the problem. What you want is to come up with a topology for which the rate is very fast, for which the convergence is very fast. And that's appealing, because if it takes forever to converge, that means you need lots of iterations. And each time you iterate, that means each sensor communicates with other sensors, and you spend power, you spend resources. Okay? So if you reduce the communication, the number of iterations required, you are going to have a much faster convergence. You are going to spend much less energy. Okay, so let me simply say this only captures, this is a very simple analysis. So this is the algorithm. Okay, you start with some initial state x0, and you iterate through this. So eventually the xi is simply wy to x0. And what you want is that as I goes to infinity, you want this wy essentially to go to a vector, to an outer product of two vectors. This is a vector of ones. This is a vector of ones. So this vector here, when you hit that one transpose with x0, you essentially add them up, add all the initial states. That's what this one is doing. Then you average that. You add them up, you average. So that's what we wanted. And then this one places that copy of the sum of the average at every sensor. Okay? So that's what the convergence here means. This is going to go to infinity, the I is going to infinity, and this Wi should converge to something like that. Okay? And that's work that people have demonstrated, Tsitsiklis and others have demonstrated that does happen under mild conditions. Okay? So that's not the work here. So let's now look at the solution. So what's the problem now in terms of the W matrix? I told you the W matrix has zeros where sensors cannot communicate among themselves, and has some weight if a sensor can communicate with another. So the entry Wij of that W is the weight if I communicates with J, and is 0 if I does not communicate with J. Yeah?
Do you have any assumptions about the density? Because for this distributed averaging, they have to have some overlapping detection area, right? Mm-hmm. So they have to be close enough to each other.
Okay, so what
to
you
sense the same event, you know.
Right. I'm assuming that all of them are measuring, are inferring about the same property of the environment. Okay, so suppose you are monitoring this campus, and suppose the campus is absolutely no one is inside the campus. Okay, suppose there were 3 o'clock in the morning and everybody went home, as if home was not here, but let's assume it was not. Okay, and you had a bunch of sensors. The only thing you are interested is, and suppose it's absolute silence. Okay, if nobody is on campus, it's absolute silence. The only thing you are interested is, the sensors are acoustic, is there sound in this campus, which then you will make a decision if the sound is wind blowing through the leaves of the trees, and in which case there is no intruder, or that sound is because someone came with a motorcycle and decided to go through the campus. Okay, so that's the problem we are dealing with. So you are monitoring a space, the sensors are making the same measurements of the same physical quantity, and they are going to try to collectively come up with a decision. An intruder came into the space, an intruder didn't come into the space. That's all I'm saying. Okay? Of course, if you are monitoring this physical space and you have all your sensors downtown in Raleigh, then those sensors are not useful. Okay, so we assume that the sensors are measuring the same physical quantity, so in that sense there is some proximity among the sensors.
They are close, I mean, they are enough to monitor the whole area, right?
We assume so. It really, that question has more to do with how reliable is my conclusion based on the sensors I have. If I have only one sensor, and that sensor needs a blow up of 20 tons of dynamite to react, then that only when you have that event is the sensor going to be useful, okay? But so the question that you are referring is a slightly different question. The problem we are addressing is, based on the information we have, compare that with the centralized one, which we know that both will converge to the same thing. The probability of error could be very high, very close to 1, but that's life. The only thing we care now is how fast does this iterative algorithm converge to the other one. Okay? Now, so the solution really is, you can look at this problem this way. So you have a graph, and what I want is to know where I put the edges of my graph. You associate it with the graph what's called adjacency matrix. So you put you label the columns and the rows by the sensors. So say sensor 1, sensor 2, sensor 3, sensor 1, 2, and 3, and you place a 0 if the sensor does not have an edge to that other sensor. So we said that there are no self loops. So sensor 1 does not communicate, does not have an edge to itself. Sensor 2 doesn't have an edge to itself. Sensor 1 does not have an edge to 3 in this case. So there is a 0, but does have an edge to 2, so you place a 1. Okay? Yeah. 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 That has to do with the undirected nature of the graph. The weights the weights are going to be positive, yes. Yeah, eventually you could associate it with this Markov chain. So from this adjacency matrix, you construct another matrix which is called the degree matrix. What this degree matrix does is counts the number of ones on each row, places on the diagonal. What that means essentially is that this matrix tells you how many communication channels each sensor has available. Okay? We are going to make a simplification which says that every sensor has the same number of channels available. Okay? So that means that we'll have D to be an integer times an identity. And then you form this other matrix, L equals D minus A. L is called the Laplacian of the graph, and it's the degree matrix minus the adjacency matrix. And I'm sorry that we have to go through this crash course on graph theory, but the reason we go is because we are going to solve this problem of the topology design, which is essentially a combinatorial problem. Where do I put, if I have, say, 100 sensors and I have 400 edges, where do I put my edges? Okay, that's a combinatorial problem. We are going to solve that by actually looking at the eigenvalues of this matrix L. Okay, the eigenvalues have to do with the spectral properties of L, and so this leads us into the solution of this topology is going to be in terms of studying the spectral properties of this matrix L. Okay, now the matrix L has a very nice object. Is a positive semi-definite, which means one actually of its eigenvalues is 0, and that's because of the structure D minus A. So if you add multiply this L by the whole one matrix, the whole one vector, you are going to get zeros. So the lambda 1 of L is equal to 0, and then you have you can order, because it's positive. You order your eigenvalues, lambda 1, lambda 2, lambda n. It turns out that the second smallest eigenvalue is strictly greater than 0 if the graph is connected. Okay, so that's a property of this. So, and so that's what. And you can. There is a beautiful book, costs $19 or $18. You can get it. Spectral graph theory that tells you this in the first chapter. Okay, so all you need to read is the first chapter, but you can read more because the book is really, really very nice. And so what's the problem that we are trying to solve? Well, the problem is, as I said, we are trying to optimize the convergence speed as a function of the graph. By the graph, I mean finding where I should place my edges. And once I put the edges and fix the topology, I also want to optimize the weights. Okay? Now we are going to use results available in the literature, in particular a paper by Shaw and Boyd, or they have several papers, but let's say that particular one, 2004, where they consider the problem where topology is fixed. So you know the topology, and the only thing they optimize is the weights. So we use their results, and in particular they show that you don't need to really have the weights can all be the same. And they provide you with an optimal value for the weight if they are all the same. And so we'll take the W to be I minus an alpha star L, where L is that D minus A. And the alpha star that Shaw and Boyd provide you with is 2 over lambda 2 plus lambda n. Remember, we are assuming a connected graph, so lambda 2 is strictly greater than 0, and lambda 2 is the smallest eigenvalue, lambda n is the largest eigenvalue, and that's the optimal gain. So what we are going to do really is we are going to look for the topology. Once we have the topology, we have the optimal gain. So we don't really need to do optimization on the gain. okay, because the gain is provided by this, because this is fixed topology, this is the optimal gain. So you could imagine an algorithm like this. Try all possible topologies. Each time you try one, you immediately do find the lambda 2 and lambda n, plug it in there, and you have the optimal W, study the convergence of that algorithm, and that would give you a number for SC. Then pick another topology, do the same, and you could do that. And of course, that would be fine, except that you'd be forever and ever again, because just for any reasonable sensor network, this should be an extremely computational complex problem, doing by search. So, what I'm going to do is try to look at, as I mentioned at the beginning, 4 classes of problems. The first class is the one that I just told you. Find the topology exactly as I told you. So find the structure of this matrix. By the structure, I mean what sensors communicate with which sensors. So find where I place the zeros there, and the non-zeros are going to be determined by that alpha star. Okay? So that's the problem that I spent the last 20 minutes talking about. Another problem, more realistic than this, assumes that there is noise in the communication. So when a sensor broadcasts its state to the neighbors, there is noise in that communication. Okay? What's the impact of this into that solution? Another one is what I call here a random, the links fail at random times and they come back at random times. And this could be because, for example, the protocol supporting the communications is based on some window and you keep repeating the transmission, but once you hit the transmission, then you stop. And so you don't, in that case, there is no communication in that particular time frame, okay? But then the next time around, you could repeat you could now transmit the state. And so this is random links. We call this random topology, okay? And finally, a more realistic case is you'd also have random links, so the links may fail, and you also pay a price in terms of the communication, okay? And this is, for example, if a link is very far away, it requires more power to reach that link than if the link is very close nearby physically, okay? So as you go from here to here, you get more realistic. But as I said, the solutions to the problem are going to be, are going from, quote unquote, a analytical solution to a algorithmic solution, okay? So let me consider the first problem. And the first problem, again, if you go through the analysis of the W power I, if you look at the xi minus x average is what you want, is that summation, 1 over n summation of the L, the initial states, and you want a copy of that at every sensor. If you look at the evolution of your iterative algorithm, it's easy to find that you can bound that by the initial error times some rho to the power I, and that rho is essentially what's called spectral norm of the matrix W. And regardless of what it is, you can work, it's trivial algebra here. You can work that this rho that governs how this converges, the speed of this convergence, is essentially 1 minus lambda 2 over lambda n, 1 plus lambda 2 over lambda n. So you want this rho to be as small as possible, okay? Because as you raise rho to the power I, that number becomes smaller and smaller. And so when this is small enough, then you say you converged, okay? So the smaller rho, the faster the convergence. So you want rho to be smaller. If you call lambda 2 over lambda n a gamma, you can go through this. Minimizing the rho means maximizing the gamma. Okay, you can look at that. And so what you want is to find the topology that maximizes the ratio of the second eigenvalue over the last eigenvalue. That's what I mean that I use the spectral properties of graph, the spectral graph theory, to solve this problem. So we look for topologies that maximize this gamma, okay, this ratio. So what's interesting is that there are available results in graph theory that can help you solve this problem in a closed fashion, okay, in an analytical fashion. So I can't go through all these details, but let me say, and this is a tricky point to understand, okay, let me say that there is a result, an asymptotic result, okay, asymptotic in the sense that as the number of sensors grows, okay, so this is for sensor networks where you are growing the sensor network. And as long as the network is what's called regular, which means that every sensor has available the same number of channels, the same number of edges, leave out the same sensor. It turns out that as n goes to infinity, this lambda, which I'm going to call lambda, but could be either lambda 2 or lambda n. I'm not going to go into the details, okay? For the adjacency matrix, as long as the graph is connected and regular, it turns out that this, asymptotically as n goes to infinity, is above a 2 root of k minus 1, where k is the degree. What this means is that those lambda 2s and lambda n's that I'm interested in, or the ratio of them, but the lambda 2s and lambda n's, as the network grows, they are going to evolve somehow, and eventually as n goes to infinity, they stay above some level. Okay, they stay above. And this is for any graph. Give me any graph that is connected and regular, and there is a nice result by these two, Allon and Bopana, 1980 something, that essentially shows that.
This is assuming that the degree of all
the degree is constant. Right, degree is constant. Okay? When the degrees are not constant, I have you can show that it's better to have degree constant than not constant. Okay, but this is the thing: is that for any, this lambda of the A comes above. Okay. Yeah.
What's lambda A? What definition of lambda A here? You mean the largest non?
This lambda.
Yeah.
Take it as lambda 2 or lambda n.
Okay.
Okay. In some cases, could be lambda 2. In the other case, could be lambda n.
I try to understand the sentence there. What do you mean by the largest and non-trivial?
Yeah, that's what I mean. The largest non-trivial means because they are ordered. This is the A matrix. Okay. Let me just say that it's either lambda 2 or lambda n, and we can offline. I can explain why that sentence means either lambda 2 or lambda n, but it would take a little bit of explanation. Okay.
Sort of understand.
Yeah. So. However, there is this gentleman called Ramanujan. Now, who heard of Ramanujan? I'm sure that many of you heard of Ramanujan, right? It's a 1920 or 30. He must have a dream, okay, or should I say a nightmare, okay? And he said, okay, let me say that I'll consider graphs for which the lambda A, the same lambda A, is smaller than this. Okay, let me think of that graph. Now the question that I ask you is this contradictory to the other? Is this class of graphs empty? Because look, here we have lambda A less than or equal to. In the previous one, I told you that is greater than or equal to, except that this is an asymptotic result. This is for n going to infinity, while this is valid for any n. And because you have an equal sign there too, that means that the Ramanujans are eventually going to the bound from below. They could jump around, but at some point they go from below. While all the other graphs that do not satisfy this property jump around and eventually go from above. Okay, so it's in that sense that I'm going to say that you can manipulate these things now. Okay, but the result is this: you can manipulate this, you can bound the gamma for the Ramanujans. Okay, so the gamma for the Ramanujans is always above that. Okay, and so it's in this sense that I say that the Ramanujan class offers you an analytical solution to the problem of topology design. Okay, so it's in that sense that the rate of convergence, the gamma that you want to maximize, is always above this, while for any other graph that you bring to me, asymptotically, it's going to go below that, asymptotically. Okay? Now, it doesn't mean that you cannot come up with a graph for finite n that beats a Ramanujan in terms of this gamma. Okay, but asymptotically, as n is large, this you cannot beat the Ramanujans. Okay, so that's a solution for the first type of problem. And the next question is, okay, so Ramanujan dreamed of these graphs one day, and so the next day I'm sure he sat down and he drew a Ramanujan graph. That's not true, because it took maybe 60 years to come up with a construction that showed here is a graph that satisfies the Ramanujan. Okay, and actually the mathematics behind it are very deep, are not easy mathematics. And you read it, and if you are familiar with the Fermat, the proof of the Fermat theorem, you see that the mathematics touch. Okay, it's similar things are floating around. The other interesting note is that these guys were at the Institute of Advanced Studies in Princeton, and they came up in 1988 with a construction. Okay, the same year, a guy called Margulis in Russia came also with the same construction. And I think that in terms of publication date, actually Margulis is earlier than Lubotsky, Phillips, and Sarnak. So I'm not going to go through the construction of these graphs. Okay, it's a challenge to read their paper, but after you invest enough time, you learn how to construct, and then you can program it very easily. Okay, because once you understand what the construction is, it's very easy to come up with the Ramanujan. So I won't go into that. Here is a Ramanujan. Okay, now you look at this and say, gee, what kind of a practical sensor network is that one? Because the sensors are all in a circle here. That's not a very useful. Okay, that's only an illusion of the display of the graph. Okay, so you go to this program, PageJack, try to play with it, try to give it a graph to display, and you move around the parameters of the display, and you can move these sensors wherever they are. Okay, so this is more like a topology representation of the graph. Okay, but doesn't mean the physical position of the sensors have to be around here. The physical positions can be anywhere on this plane. Okay, but you look at that, you stare, and you see no structure. So you could not sit down at home and say, I'm going to come up with a Ramanujan, because I've stared at this and I can't see any structure. And this is a small one. This is only 60, because to have some indication of representation. Okay, if you put
they all have the same degree.
They all have the same degree. Yeah, they all have the same degrees. So let me now show you how does this compare with other graphs. Because I told you asymptotically the Ramanujans are optimal, but what happens for finite n? So we chose 3. I'm not going to go through the details. This one here is one where you essentially think of the sensors as pixels in an image, and they are connected by nearest neighbors. Okay, so each pixel connects to the 4 neighbors and so forth. Okay, so that's this type of structure. If you were asked, if any engineer, human with no knowledge of the problem were asked, come up with a topology, that's what you do essentially. I'd say I'll communicate with my nearest neighbors and each nearest neighbors. This is a random graph, and this is a random graph, but is what's called has small world characteristics. Okay, and let me just show the results. This is the case where I'm comparing the speed of convergence of the Ramanujans with the uniform grid kind of thing, like the images, the pixels in an image. And what you see is that as the number n grows, say from 1,000 to 2,000, the speed of convergence of the Ramanujans over the other one is much higher, so it goes from 300 to almost 900, okay, or 800. So it's almost 3 orders of magnitude. So what this means is that the number of iterations needed to reach that understanding of the environment, if you use a topology like the Ramanujan, is 3 orders of magnitude faster than if you use your intuitive kind of topology. Okay? So And if you compare with the others, I'm not going to go, let me just compare for the small world. The small world do pretty well, okay? Still the Ramanujans do better, about maybe 20 or 30% better than the small world. The small world, I would need to spend some time explaining this, but I don't have the time. So the message is just that the Ramanujans are much better than the regular structure, and they are better than some other structures that people thought they were very, very good. Okay, these structures are very good, the small world are very good, but the Ramanujans are actually smaller. And there is a lot of work in designing these, while these, once you know how to construct them, they just come like that. Let me consider very quickly the other three problems. So the first one was you add noise to your communication. Not going to go through all the details. I'm just going to tell you what the implication is. The implication is that essentially, because of this noise here in the communication, your iterative algorithm is going to have an optimal number of iterations. You should not iterate forever, okay? Because essentially, this state is going to be random now because of that, and the variance of this state is going to grow, okay, and grows linearly. There is a term here that is linear on the number of iterations. So if you parse this expression, you would see that the variance first goes down as you iterate, but then starts going up. And so there is an optimal number. So the impact of that is essentially saying your iterative algorithm should not go forever, should have a finite number. Let me skip the random topology and go to the last one, which is the random topology and with the communication cost. So, because this includes the previous one, and so I'll spend a few extra minutes on this one. So, the model here is that the links may fail. Okay, so remember the algorithm progresses as an iterative algorithm. So at every iteration, sensors communicate among themselves. Then they update their state. Then they repeat the communication, update the state, repeat the communication. So what I'm saying that the links fail is at each iteration, when a sensor starts communicating with others, a link may fail. When I broadcast my data to someone else in this room, that link may fail on this iteration. On the next iteration, the link may come up. Okay, and they come up and fail with random, like flipping a coin. Okay, so that's the model. The other thing is that the links may have different communication costs, and this is immediately connected to the physical distance. Okay, if I'm communicating with the sensors very close, geographically very close, then I don't expend as much power. If I'm communicating across the room to the back, then I need to speak louder, so I'm expending more power. So there is a communication cost, and we capture that communication cost by a matrix C. Just like I was talking about the adjacency matrix of the graph, now I have a C. And each entry in C is the communication cost between I and J. Okay? And we place a constraint on the communication cost, meaning there is a global budget for the communication. So, and it's on an average because the topology is random now. You can show that essentially the overall communication cost is going to be the trace of C times L, but you take an expectation because you want to do an averaging, and so you place a constraint that is an average communication cost. Okay, so each time I communicate, it's like I have a budget U bar, okay, and I'm going to assign that budget to the different sensors.
L is your Laplacian, right?
L is the Laplacian, but the L is random now, okay, because the topology changes, right. Okay, and because there is this expectation C is supposed to be fixed, so this E comes to the L, so essentially your budget is a trace of CL bar with a minus sign here, okay, and so the problem now becomes trying to optimize the rate of convergence was some spectral norm, as you may remember, of some rho, okay, subject to the constraints that this L bar has to satisfy this thing here. Okay, so this L bar. So the problem of topology design now is really, given the probability of link failure is to look for a P matrix, the P meaning the probabilities of link failures, which is intimately related to the L bar, is looking for an L bar on average, which sensors should communicate with which sensors, such that this is satisfied. Okay? So that's the problem of topology design with random communication costs. And you can show that now there is no analytical solution. You can't come up with a Ramanujan. Even Ramanujan couldn't come up with a solution to this problem. Okay, not that he knew when he invented the graphs that they would be the solution, but anyway. The problem, but you can show that it's a convex optimization problem and that there are nice algorithms that you can use here. So I'm not going to go to show that. Let me just show you the results. And the results are here. So what we did here is we assumed the Poisson number of sensors, and then we distributed those sensors uniformly here. I don't remember how many sensors, 80 sensors. Okay, and we assumed that we wanted to design a topology with a regular topology of 9 links per sensor. So each sensor can communicate with 9. And there was some communication cost C, which I haven't written here. The C can have infinite entries, okay, which means if you have an infinite entry on the C, that means those two sensors can never communicate. Okay, it's too expensive, you can never communicate. And so basically, what you look is with certain probabilities P's of establishing these links, okay, we are looking for that L bar, that on average the structure of the topology. And what these things show here is, in this case, you have the nearest neighbor, the nearest neighbor kind of thing, and this is the rate of convergence, and this is U bar. This is your budget. Okay. What this shows is that if you have a lot of power to communicate, a lot of you can allow a very large cost, then basically in this case you can allow all the links to communicate among all the other links. Okay, so you can pick the best, and basically these two curves are going to converge. However, if your budget is limited and there is kind of a threshold, say at 8 or at 7, somewhere here, okay, if you have a limited budget, it pays you to have this L bar that we came up, and if you analyze the structure of this L bar, it tells you that from time to time it pays you to pay a lot and go across and not just use local communication, but go across the room and talk to someone else far away. Not that you do that all the time, but from time to time it pays you to go across. Okay, and that's what this blue curve is telling you. Okay, that's basically what this. So of course, if the U goes to 0, then both of them. If you don't allow any communication at all, then of course both also go to 0. Okay, so these two curves are like that, but you see that the topology with communication costs you can allow. There is some gain by looking at topology designs. Okay, so. I'm sorry that the last problem kind of it's not very well explained. I ran out of time here, but let me just say that I explained to you the topology design problem. The problem is solved in the context or is formulated in the context of spectral graph theory, because essentially you are trying to design a graph or a certain matrix associated with the graph whose eigenvalues are extreme in some sense, okay, or some parameters of the eigenvalues. If you look at non-random topologies, you have this very nice construction of Ramanujan graphs, and that leads to several orders of magnitude over an intuitive kind of topology. if you go through if you start adding noise, or you go through random, or you go through communications, you get some results not as nice or as clear as in this case. However, the results still fit nice numerical optimization problems for which you can use SDP kind of strategies or algorithms. And that's, I think I'm going to stop here.
Well, we have time for some questions.
So,
Yeah.
the SDP, can it be implemented distributively?
Yeah, the SDP with okay. If you mean, is it implemented distributed in the sense, this is an a priori kind of problem. The way we look at the problem is you are designing a priori. It's not that the sensors adaptively find their topology to communicate. Okay, so the way you implement SDP depends on your computer, the computers you have available. Okay,
So
and
if the sensor, a new sensor
Can you speak
enters,
into this?
and you need to do it again. So
it's a one shot. It's a one deal. It's a one deal. So what you are addressing is the following problem: is that you assume that the sensors were deployed and the sensors don't know where they are. They have to find where they are. Then they determine the topology, and maybe then some sensors fail, and then you want to find the new topology again and again. No, that's not the problem here. The problem here is a simplistic problem. Assumes you deployed, you know where the sensors are, you are at home, you have your supercomputers there, you go through all these SDP kind of computations, you find the topology, you tell the sensors you communicate with X, Y, and Z. Okay, so that's the problem we address. Yeah.
Yeah, my problem is somewhat related. So is it possible to effectively control the topology for pre-existing sensor networks?
If I'm sorry,
It is feasible to effectively control the topology for pre-existing sensor networks,
Okay, so
like through like a mag layer or network layer.
oh, I see
protocols.
what you mean. That I leave up to you to answer. You are the MIMO guy here. So I understand what you are saying as if I'm going to communicate with the person in the back room, am I not broadcasting here so that everybody else listens to our conversation, right? Yeah, that's another issue under the rug.
Any other question? Yeah.
Actually, my question is, I think, is related to this. And the last problem we talked about communication costs, right? So in the first two, non-random topology, so we assume the communication cost is fixed for all.
Right.
But we have, for example, all the nodes have same degree. So
Right.
how we are assumed that
So
all
you
the
are
nodes have same degree and all
right.
have same communication.
I understand. You are absolutely correct. First, in the first three classes of problems, we assume the cost to be the same for everybody. Okay, so that's an assumption. That's only raised in the fourth. So you could look at the first three problems as building blocks to understand the problem and then address a more practical problem, which is the fourth one. So you could say, forget about the first three, just look at the fourth. But as you know, there are insights that you gain by looking at simpler versions of the problem. And your other question was?
That's
Okay, so yeah, I'm not saying that let's deploy this strategy and connect topologies. What I'm saying is, does this provide some insights in terms of how should we communicate? So for example, going back to your question, suppose you are in a crowded room, okay, and everybody's talking and very loud and so forth, okay, and a rumor is started in the room. So the issue is, how many iterations do we need to iterate on this rumor, okay, till everybody kind of guesses what the rumor is or says, oh no, forget about that, okay? So the issue is, if there is enough noise that when I communicate with the person in the back, I may scream, but really everybody is so busy talking to their friends that they don't listen to me, even if I scream, okay? So that's more, that would be a practical, or another one is on virus spreading. Okay, suppose you have virus spreading. And this tells you a little bit on how fast. So if you don't travel, and this is obviously intuitive, right? If there is a disease that starts, so the avian flu or whatever, and people don't move, they stay put, the avian flu there can be a focus here, that can be a focus there, there can be a focus there, no big problem. Only for the local populations, of course. But now you start having people from time to time jumping on a flight and go like they did, where did they go, to Minneapolis or to Toronto, okay? And immediately starts a focus there. And then they went to New York and they immediately starts a focus there, okay? So that's another type of problem. Now, how does that translate into sensor networks? I agree that we still have more work to do.
Is that related to the small world effect?
Yeah, that's related to the small world. But if you did it Ramanujan-like, then you'd beat the small world even fast. So you want to avoid that for these other problems.
I have one question. So how easy is it to sort of add more than one constraint? Say, for instance, you wanted the communication, and you wanted, for instance, let's say power. You want to have power constraint. Is that easily taken into account in terms of reformulating the problem that you showed at the end?
Okay. So, as you know, when you get into combinatorial problems, the issue is fast algorithms to find the solution. So, whatever constraints you bring, they have to somehow keep the problem within a convex optimization, okay? At least that's the way, as far as my knowledge goes. Yeah. So the issue is you have to be very careful in crafting the problem. Okay, so if you come with arbitrary constraints, then the constraint might lead to a non-convex optimization. But when we were looking into this seed, we were lucky, I think, that it led to a convex optimization problem. So depends on the constraint and depends how you craft it into the problem. Okay, so my answer is to yes, but. Okay. Yeah.
Yeah, Brian.
Yeah, I was just wondering if you have any insights into how the answer is improved if you allow W to vary with time.
Yeah, that's a very good question. Yeah. Now I'm speculating, okay? I would say that if you look at the structure, the xi plus 1 equals wxi. So if the w now is a function of I, okay, let me give two answers there. If it's a random, like in the L case, the third case and fourth case, then everything becomes in terms, under the very simple model of randomness where you flip a coin for each link, okay? Then everything becomes in terms of the average topology, okay? So there is some time variation there captured by a random effect, and everything translates into the deterministic problem because it's into the average topology. Now, but I think your question was different. I think that your question was rather than just the topology changing, my gains are going to change over time. So there, what the insight I would have is like what you are asking is like a similar question would be in a linear system, asking where the matrix, so x dot equals ax plus bu, if you are familiar with this terminology, is like the a being time varying, and you are asking for stability type issues on that system. Okay, because that's really what we are asking is an asymptotic stability of the xi plus 1 equals wxi. And if the w is time varying, you are asking for an asymptotic, for the moment, or for the the mode of that system, the slowest mode to die fast enough. That's what this is telling you. It's the slowest mode. So now, if the entries of the matrix change with time, you'd have to study that in terms of stability of time varying. So I'm sure that the people in this topic of studying these algorithms, which go by the name of consensus algorithm, has actually been a big topic for the last 4 or 5 years with the CDC, with the Controls Conference. And so I'm sure that there people are looking at problems like that and using Lyapunov functions to study stability and things like that. But I'm not familiar with their results. Yeah.
Last question.
Yeah, I noticed that you mentioned that there exists an optimal number of iterations in the algorithm. I'm just wondering, why is that? Any intuitive explanation for that, or it's a general conclusion for the, or this is just special for this consensus, the distributive consensus algorithm?
Yeah. So if you have no noise in the communications, okay. If you look at one of the slides here. Where was it? This one. If there is no noise, you see you have rho to the I times this, and so this as I goes as you increase, this is asymptotically. So each new iteration decreases the error here. Okay, so you are asymptotically and monotonically going to the limit. So the more iterations, the smaller monotonically. Okay, so in this average consensus distributed algorithm, the more iterations, the better, and it's monotonically decreasing the error. But now, if you put noise, okay. So let me go now to the. If you put noise, if the communications has noise, okay, you are adding uncertainty to this. So if this is not there, this is going to converge to the value that you want. But because now you are adding noise, you are trying to converge as you iterate, but you are adding variance. You are adding variance to this state. Okay? And so basically, if you look at the variance is going, so this part here, forget about all that. I think it's this part here is due only to the fact that you are iterating. So this part here as n goes to, as I increases, this is going to go to 0, and this is the limit variance that you get due to your initial uncertainty. Okay, but now when you start adding this noise, there is this other term. So at some point, this is going down, this is going up. So it's the one trend going down, another going up. Essentially, they cross, and when they cross, you have the optimal number. Okay, so it's because this is due to the noise, this is decreasing due to the iteration. Okay, but after a while, this takes over and dominates. Okay, that's why you have an optimal number. Yeah.
Okay. I'm interested to know, do you really consider the practical solution about how nodes exchange their current value? Let's say you're using iterative equation Si plus 1 equal to WSI, right? Because some nodes maybe currently keep the value of S plus 1, and some other nodes keep Si. Your equation is perfect based on synchronization.
Right. Perfect
right?
synchronization.
And, but in practical, some nodes will definitely get the value earlier than others. And once the nodes keep increasing the number of nodes, this kind of iterative communication will cost a longer time.
Yeah. So let me tell you 2 or 3 things there. Or one. So this problem can be complicated, the version of the problem that I gave you, by considering asynchronous communication. And by mixing all the things. Look, the way I formulated, when I dealt with noise here, I didn't say that I was dealing with the random. Okay? So I did noise here, then I did random topology. I didn't put a case here where I had noise and random topology. And I didn't say anything about synchronization. I didn't say anything about delays in the communication. All these, when you start mixing, for example, noise with random links, just that, still with synchronous, the problem is very different, okay? And it's much more complex, okay? When you have, when you add to that, or to any of these versions, when you add asynchrony, or when you had delays, the problem is very different, okay? So all these are very relevant issues, and I just need a few more grad students to work on them.
All right. Well, thank you very much.
Okay, thank you very much.